My name is Scott Stoll. I do a whole lot of things that you probably won't care about. So we can skip all of that and just get on with the show. However, before we get started, is this not the coolest picture of Jupiter you have ever seen? That is just fantastic. All right. The first thing I want to do is go over where this is going, because nothing is more annoying than sitting here through a talk, not being able to understand where the whole thing is going. So we're going to go through something that I call the tongue twister, and we're going to do this twice. We're going to do it once now, and then we're going to do it once again at the end of the talk, and we're going to see if it makes more sense to you the second time than it does the first time. All right, so let's get started here. A flex is flexible, but don't confuse the fact that it can be flexible with an actual flexible. A flex fit has nothing to do with the fit of the flex. Flexes don't fit, flexibles do. The flex of a flexible determines the strength of the flexible, except when it doesn't. You can set the flex to 9 kajillion. If your flex fit is loose, it's not going to do squat. The flex of the fit determines if the flex of the flexible will be allowed to flex the flexible so it fits better into the flex. And finally, don't confuse the flex with the flex, or you're going to end up, did you think I was going somewhere else with that last one? All right, let's go over a few terms real quick. I think we're pushing the feedback there. So these are a few terms. It's probably beneath the level of this crowd, but let's go over them anyway just to be sure. The first thing is the flex. Now, it is the superclass of row and column. Row and column extend the flex, as I'm sure most of you know. Next is the flexible. Now, it can force its child to be bigger than the child wants to be, however, it does not have to. Next is the flex, the other flex, which determines the strength of the flexible compared to other things that have a flex. Next after that is the flex fit, which determines if a flexible must use all the available space. Okay? And then we have the fit, which is a parameter of the flexible that takes something called a flex fit. So let's take a look real quick at something here called available. Now, available supposedly equals leftover. I say supposedly for a reason. Okay? Available equals leftover. Okay, but let's take a little bit closer look at this. It says a widget that expands a child of a row or column or flex so that the child fits the available space. There's a little problem with this. I'm not quite sure how to put it, but yeah, that about covers it. It's a lie. It does not fill the available space. It fills the space that was reserved for it. So let's take a look at the flex layout algorithm, which is also known as render flex children have non-zero flex, but incoming height constraints are unbounded. Yeah, we've seen that a couple of times. So one thing we don't want to do is we don't want to be this guy. Okay, everything goes up in smoke. The laptop loses its magic smoke. The magic smoke is what makes the laptop work. We don't want to lose it. So we're going to take a look at the 6-step multi-child layout algorithm, one step at a time, and I'm going to translate these steps into something a human being can understand. So step 1, lay out each child a null or zero flex factor, for example, those that are not expanded, with unbounded main axis constraints and the incoming cross-axis constraints. If the cross-axis constraint is cross-axis alignment.stretch, instead use tight cross-axis constraints that match the incoming max extent of the cross-axis. Yeah. What? So let's translate this into something we can understand. First, we're going to lay out the children that have set sizes, which means they have no flex. Then, we're not setting the main just yet. Okay, yeah, the audio went a little too low there. We're not setting the main axis sizes just yet. Now, this is what unbounded constraints means. It's not setting constraints on anything because it hasn't set the main axis sizes yet. So let's take a look at cross-axis alignment stretch. If the cross-axis alignment is set to stretch, then force everything to be as big as possible in the cross-axis. Okay? Why couldn't they just say that? We're going to run into a lot of this. Next, let's take a look at step 2. Divide the remaining main axis space among the children with non-zero flex factors, for example, those that are expanded, according to their flex factor. For example, a child with a flex factor of 2 will receive twice the amount of main axis space as a child with a flex factor of 1. What? What this means is you reserve the leftover space along the main axis among all the children that do have a flex parameter set. Now keep in mind, a flexible and an expanded have a flex set to 1, even if you don't change it and set it that way yourself. So that's what it means by if the flex is not 0. Now, we're not supposed to play favorites, but we do. So maybe you like some children more than others and you want to give them more space than the others. Well, how do you do that? You do that using the flex. Not the flex, the flex. So let's look at a little math. Yes, we all hate math. Don't worry, this is not that difficult. 3 children have 3 different flex factors, 1, 4, and 5. 1 plus 4 plus 5 equals 10. The first child has a flex of 1 and the total flex is 10. This child gets 1/10 of the leftover space reserved for it. Doesn't necessarily get it. The second child gets a dinner reservation for 4 out of 10, or 40%. Then the last child gets half. So what we're going to do then at the next point is calculate the DP, which is density independent pixels. And we can calculate the actual number of DP that will be reserved for each one based on what their final share of the leftover space could be. All right, not is, could be. So let's take a look at step 3. Lay out each of the remaining children with the same cross-axis constraints as in step 1, but instead using unbounded main axis constraints. Use the main axis constraints based on the on the amount of space allocated in step 2. Children with a flexible fit property, that is flex fit tight, are given tight constraints, for example, forced to fill the allocated space, and children with flexible fit properties that are flex fit loose are given loose constraints, for example, not forced to fill the allocated space. Yeah. Let us ponder something. We are pondering. Each child's main axis size limit, also known as a constraint, is set to the calculated number reserved for it in step 2. This is the max it could be, but not will be. So let's take a look at the flex fit enum for a moment here. Note that it says the child is forced to fill the available space in tight. However, there's a key thing to remember about this. It is only in the main axis. This has nothing to do with the cross axis at all. So let's take a look at the flexible constructor. And the flexible constructor has the super call hard-coded to tight. I'm sorry, this is the expanded, not the flexible. The supercall is hard-coded to flex fit tight. Now, in the expanded constructor, it points to super, but what is the super? Well, the super of an expanded is that it extends the flexible. Okay, now remember, a flexible typically has a flex fit set to loose. Now, here we're calling the super constructor, and it extends the flexible, as we said. So what makes it an expanded? And the only thing that makes it an expanded at all is that the flex fit is set to tight. That is the only difference between an expanded and a flexible. Right there. So, next, let's take a look. Oh, I'm sorry. The default value of flex fit loose is there circled. So right here again, we take a look at it, and tight is going to force it to fill all of the available space right there. Now available, once again, means the space reserved for it, because that's what's actually available to it. So let's take a look at step 4. The cross-axis extent of the flex is the maximum cross-axis extent of the children, which will always satisfy the incoming constraints. See, I got that one done in one breath. Now this one confused me quite a bit at first, and I was very, very lucky that my neighbor was very helpful in all kinds of things that confused me. And I gotta tell you, the amazing Wanda is amazing. She was able to help me with this and straighten it right out. The cross-axis size of a rower column is going to be as big as its biggest child in the cross-axis direction. Okay? In other words, it will be as big as the largest child wants to be, or as big as its parent says to be. If the parent passes down a constraint that is larger, and it's a tight constraint, that's going to force your rower column to be larger than its largest child. Now, what if one of the children wants to be infinite in the cross-axis and the parent does not constrain it? Well, of course, we end up with an error. Box constraints force infinite height or width, depending on what you're working with there. So let's go on to step number 5. The main axis extent of the flex is determined by the main axis size property. If the main axis size property is main axis size max, then the main axis extent of the flex is the max extent of the incoming main axis constraints. If the main axis size property is main axis size minimum, then the main axis extent of the flex is the sum of the main axis extent of the children. What? That. Again, what? Oh man. All right. So looking at the dot comment, the main axis extent of the flex is determined by the main axis size property. If the main axis size property is main axis size max, then the main axis extent of the flex is the max extent of the incoming main axis constraints. I told you this is a tongue twister. In human, if the main axis size is set to max, this is the default, then the length of the main axis of your flex, rower column, is going to be as large as its parent will allow it to be. That's basically it. If it's set to max, it's going to take up the max that the parent will allow it to be. So box constraints dot max height for a column and box constraints max width for a row. So let's take a look at main axis size minimum. If the main axis size property is main axis size min, then the main axis extent of the flex is the sum of the main axis extent of the children. Yeah. Just add up all the sizes of the children along the main axis and use that. It's not that difficult. Just add them up. So then, subject to incoming constraints. You know what that means? If it fits. That's what it means. You add up all the children for main axis size min. That's the size it's going to be if it fits. Why couldn't they just say that? So this is a little bit interesting. You'll want to see something really scary? How many of you remember the Twilight Zone movie? Oh yeah, it's a little before everybody's time. So let's take another look at the flex fit enum. Again, when we take a look at it, it's forced to fill the available space or is allowed to be smaller. So let's do a little bit of an example here. Let's make a column 900 high. That's what the parent is. The parent is allowing this thing to be 900 high. The first child has a set size of 300. Okay, that size is fixed. It does not have any flex factor. So the next is an expanded with a child that is 150 high. And the next one after that is flexible with a child that is 150 high. Now, after we put in the child that has no flex, what we end up having is 600 left over, right? It's pretty simple. 900 minus 300 is 600. More math. So the flexible and the expanded are default for this, so they each have a flex factor of 1, so each gets the same amount of space reserved for it. Okay, again, it's the same amount of space reserved for each one. When they get laid out, the expanded uses everything that was reserved for it, which is 300, okay, because it's forced to take all the available space. However, comma, when we lay out the flexible, it only uses 150. Well, this is a 900 high column, right? So what happens down here? Nada, nunca, nothing. So it looks like it's 750 because that's all there is and there's nothing under it. So why does it look like this? Because flexes don't have borders. So when you look at this, it looks 750 high. Although if you add a border, whoops. I'm sorry. If you add the border right there, you can see that it is actually larger than the children are taking up. So let's take a look now at step 6. I promise this is the last one. Determine the position for each child according to the main axis alignment and the cross-axis alignment. For example, if the main axis alignment is main axis alignment dot space between any main axis space that has not been allocated to children is divided evenly and placed between the children. What? All right, main axis alignment options. We have start, center, and end. This is pretty simple. Okay, it's at the start, center, or end. However, there's a trick here. Start, center, and end are defined according to the language setting of your app. If the language reads left to right, then the start is on the left. If the language reads right to left, the start is on the right. So that's important to remember. Now let's take a look at space between. The first and last children on the ends, and then there's the remaining space in between. So the children themselves right here are placed on the ends, and then we divide the space up evenly among what is left. Now let's take a look at space around. The first and last children are padded by half the amount, and then between the others is a full amount. Now, that looks a little goofy. All right, it can even be a little bit difficult to understand unless you look at it closely. However, you can also add a couple of lines. See, what happens when we add the lines is suddenly everything makes sense. There's half the amount of space around each and every single child. It's just the way they're put together makes it look like double the amount of space in between the other children. So space evenly. That is the same space before and after every single child. All right? All those spaces are even. Pretty simple. Now let's take a look at the cross-axis alignment options. Start, center, and end. Once again, start in a row is going to be at the top always. However, in a column, again, we have a language setting that we need to worry about. Stretch is going to force all of the children to try to fill the available space in the cross-axis. So they're all going to be the same size, and that's the maximum size that they're allowed to be. Baseline. This one gets fun. It aligns the baselines of all the children like this. Well, that doesn't look like anything unusual. That pretty much looks like a row that is set to end. But when we look at the constraints, that is because the largest child fits within the minimum and maximum constraints given to it by the parent. However, what if the largest child is smaller than the minimum constraint? Do you ever think about that? Probably not. However, what ends up happening is it floats, because it will align with with start. It will align with start right there. And the bottom of it, the bottoms are all lined up on the baseline, but they don't necessarily have to touch the bottom there. So there's the baseline, and they don't have to touch. For bottom or left align, you would use start, but this lets you float, right? So you can float your baseline up off of the start. Because you can. Okay? Why would you do this? I don't know. You can. Just because you can doesn't mean you should, but if your designer wants to do that, then do it. The capability is in your hands. So let's go back to the tongue twister. Remember, Padawan, a flex is flexible, but don't confuse the fact that it can be flexible with an actual flexible. A flex fit has nothing to do with the fit of the flex. Flexes don't fit. The flex of a flexible determines the strength of the flexible, except when it doesn't. Well, when does the flex not determine the strength of a flexible? When it's set to loose. Because then the size of the children is what decides how big it's going to be. You can set the flex to 9 kajillion. If the flex fit is loose, your flex is not going to do anything. The flex fit of the flex determines, let's start that one over again. I told you it was a tongue twister. The flex fit of the fit determines if the flex of the flexible will be allowed to flex the flexible so it fits better into the flex. If that one makes sense, then I have achieved my goal. Next, don't confuse the flex with the flex, or you're going to end up all right. If you're half as confused as I am after all of that, then you probably need some help. There are plenty of places you can get help. I don't think anybody's using it anymore, but there's something called the Gitter. It is available for every GitHub repo. The Flutter team actually used to use this during alpha. It is what I call a single-threaded monstrosity because there's only one thread in the entire chat. Then there is a Google group for Flutter Dev and also a Reddit. The Reddit is actually fairly popular still. Then there's Flutter Community Medium. We have over 2,000 articles available. So that right there is a fantastic resource. Articles have been written by a lot of people who are in this event right now. I think Pooja's written about 25 of them. Then you can follow who I follow on Twitter. And on the Flutter Community YouTube channel, we have a weekly show called Hump Day Q&A, where we do a little bit of an intro and talk a little bit about what's going on in Flutter, and then we open it up to taking questions from all comers at any level. It does not matter how complicated your question is, how advanced it is, we're going to try to answer it. And Randall Schwartz right here is one of the people on the show. And also, if you've heard of Simon Lightfoot, he is also on the show, and he answers most of the questions right now because most of the questions are so complicated, a lot of us can't even understand what the questions are. But that's pretty much it. I appreciate you coming to the talk, and hopefully you got something out of it no matter what level you're at. Thanks.